This is Salcott, and I thought that today we could talk about something called the Dichotomy Paradox. Now, this is one of the philosopher Zeno's paradoxes, and it includes the claim that motion is an illusion. Now, to elaborate a little on that, the paradox states that, well, this one is within the bounds that because an object moving from a point A to a point B has to go through the middle point, and then also has to go through a middle point between that middle point and the end, and then between that, and then between that, and then between that, and between that, that they don't reach the end. But they do. Now, to kind of create an example out of this, I've chosen a turtle, which is kind of similar to a creature used in another one of his paradoxes, moving from a same point A to point B. And we're going to use a little bit of differential calculus to figure out kind of what the answer is, but the answer won't be very satisfying because it's still a paradox and a lot of people have tried, and this is not a final solution or anything. Now, I've created a graph here where my y-axis is basically equal to the distance y-axis is the distance traversed, right? And then my x-axis down here is equal to the little trips made, the little increments of space that that the turtle goes through. Every tiny little trip. Let's say he goes the first time halfway, stops and rests, and then he's too tired and only goes half the distance between halfway in there, and then half of that distance, and half of that distance, and then half of that distance. Now, just let's try to derive an equation out of this. So, f of x is equal to, well, let's see, it's obviously growing exponentially, and it's shrinking exponentially, not growing. If you're growing by shrinking, then you'd be growing, but no. And since we're dealing with the distance traversed, we're going to be subtracting a certain smaller distance every time because we're getting farther. And that means because we only have, I've made it 1 unit to go. I don't know why 1 unit, just it's convenience. Minus, because 1/2 to the x power. And what this is saying is basically the more trips you make, you go smaller and smaller and smaller distances, right? And you're also subtracting smaller and smaller and smaller distances from going the whole distance. You're never quite there, right? But you're still moving, so shouldn't you get there? Well, according to this, you shouldn't. Not exactly. So, let's try to graph this and see what we think this is really saying. So remember, this is the distance traveled. This is the number of trips. So after 0 trips, I've already graphed it here, you've gone 1 minus 1/2 to the 0th, 1 minus 1, you just had 0, right? 0 distance traveled, 0 trips made, that makes sense. So when it's 1 minus 1/2, you've gone 1/2, right? Pretty obvious, right? Now, if we continue to do this, and I'm not going to do every one for you guys out loud, but, you know, minus 1/4, you have 3/4, you have 0.75, right? And then this just continues. Right? 1/8, and then it just, as you may be noticing, you're going half the distance that you had to get there every time. And that is kind of frustrating for this poor turtle that's been walking from point A to point B for its entire life and possibly eternity. Let's find out. So if we go to the next one, right, we're still getting closer though. But we're not quite there yet. The coordinates are just big for just visual assistance. Now, here's the problem. We're going so slowly at this point. We're not going like any distance between these rests. This turtle is exhausted. Okay, I'm going to stop using the turtle analogy, but it's just useful to have a kind of practical envisionment of all of this. So, just let this continue. Every trip, we're going such little space, it's even hard to see. But we're still getting closer. But, here, let's just make this clear. This is always above. The coordinates are kind of big, so it arced a little, but it's always above. Just remember that. So I'm not going to do all 30 of them because there's really no... Well, why not? We're close. I don't think I've done 30, but it gets the idea across. And it is accurate, I assure you. We're always going up. We're not going down. Not going down. It may look like it sometimes, but we're not. We're always going up. We're just going up at such a tiny increment of space that it's impossible, almost with our eyesight and our detection, to tell that there's any difference, except in my bad drawing. Okay, so let's graph this whole function. Let's connect these dots. Alright, it starts to curve. Starts to curve around here. Starts to curve and continue. Go and get closer and closer and closer and closer and closer and closer, ever so close. There's a little divot here that's not supposed to be there. That was an accident. Okay, so at here, let's draw our arrow. Show. That's just going on forever. Forever to infinity, and that's important. That infinity there. We'll get to that in a second. So, when does it reach 1? How many trips does he have to make to go the whole distance? Well, let's see, using something called the limit from differential calculus, which is basically just where is somewhere approaching as somewhere else is approaching a certain value. So, our value that's approaching something, I'm saying approaching a lot, but that's really what a limit is. So our limit, as we want to know, when f of x, you could write the whole equation, but we have it right there, so why bother? Nears 1, right? We want the distance traversed to get to 1. And what does that mean that x equals? So the limit as that nears that is being taken of x. What's the limit of x? What is x's limit? Like, really, what is it limited? What is it not allowed to become as f of x starts to become 1, which it won't? Exactly. So, how do we solve this? Well, because as x gets larger and larger and larger, you're subtracting smaller and smaller and smaller fractions, and you're getting closer and closer to 1. So obviously, as x is getting larger, you're getting closer, right? And let's try like a billion, like 1 to the billionth. It's, that's amazingly big, and I can't do it in my head, but it's very, very, very large. It still has a value, though. It's still 1 over, trillions and trillions, whatever. It's still 1 over that. It's still a tiny value. But let's think of the largest number imaginable that nothing can even be equal to. How about infinity? Now, infinity is used in limits a lot because it's useful to determine y asymptotes and x asymptotes, which is basically as x gets to 0 or x gets to infinity, usually, or the denominator basically gets to 0, which is infinity, something divided by 0. It's just, it doesn't make sense. Or if you have x is equal to infinity, then all the other terms don't really mean anything anymore. And you can find what y is when x is equal to infinity. Y or f of x or, the function of x. So, we wanted to get smaller and smaller and smaller and smaller. So the limit, because nothing can equal infinity really, because it's larger than anything, if you go a very large distance, you're you can't get there in any case. So the limit is equal to infinity. Now, if this was like an integer, it would be negative infinity, right? Because you'd want it to be exponentially growing smaller down into the decimal places. But because it's already a decimal, you can just multiply it times positive infinity, exponentially multiply by positive infinity, and it will go smaller and smaller and smaller. It will become decimals of decimals of decimals of decimals of decimals, and etc. So let's think of this the other way around. The limit, just kind of to prove it, as, or the limit of our f of x this time, we can write the whole thing out now, 1 minus 1/2 x, now we're just solving to be sure, as x approaches the infinity we promised, right? Well, let's see, 1 minus 1/2 to the infinitieth. 1/2 times 1/2 times 1/2. Since the numerator is 1, it's always just times 1, it's not going to change. But the bottom, that will change a lot. 2 times 2 times 2 times 2 times 2 times 2 times 2 is not that specifically, but endlessly to infinity. 2 times itself and itself and itself and itself, again, infinite number of times, for an infinite number of times, is going to be so outrageously small. This we can just consider mathematically is equal to 0. And then we get the distance traversed is equal to 1, right? 1. This is our f of x. Our limit of f of x as x gets to infinity is 1. We've basically gone the distance after infinity. But this is an infinite number of trips, and it's still not quite the whole distance, is it?